All right, today's lesson is going to be on 5.3 linear, quadratic, and exponential models. We're going to start off by comparing a linear model. On a linear model, we'll have this table. 0 is 3, 1 is 5, 2 is 7, 3 is 9, and 4 goes to an 11. On a linear model, you're going to compare the first difference. The difference between 3 and 5 is 2. 5 and 7 is 2. 7 and 9 is 2. And 9 and 12 is 2. So because the first difference are all the same, that's why this pattern is going to be linear. Now you have this equation y equals mx plus b, where 2 is going to be the slope because that's the change. Now the y-intercept is when x equals 0, so the y-intercept is going to be 3. And this would look like this. You have a y-intercept at 3, and then it goes up 2 over 1. So when you're comparing a linear model, if the first difference is constant, so you see how it's constant, then it's linear. We are now going to compare it with a quadratic. We have 0, 0.25, 0 and 1, or actually 1 and 1, 2 and 2.25, 3 and 4, 4 and 6.25. When you compare the first difference, I already know this is not going to be linear. I know the first difference is going to be different just because I flat out told you it's going to be quadratic. So right here, when you do the first difference, the difference between 0.25 and 1 is going to be 0.75. And the difference between 1 and 2.25 is going to be 1.25. The difference between 2.25 and 4 is going to be 1.75. And the difference between 4 and 6.25 is going to be 2.25. So they're not all the same. So now I'm going to take the second difference. The difference between 1.25 and 0.75, if you subtract them, it's going to be a 0.5. The difference between 1.25 and 1.75 is going to be 0.5. And the difference here is going to be 0.5. So notice how these are all the same now. So the second difference is the same. So on a quadratic, it's going to be y equals ax squared plus bx plus c. That is the standard form. Now on this one right here, the equation is actually 0.25x squared plus 0.5x plus 0.25. And if we graph this, at 0, it's at 0.25. At 1, it's at 1. At 2, it's at 2.25. At 3, it's at 4. 1, 2, 3, 4. It looks like this. On a quadratic, if the second difference is constant, then it is a quadratic. And the last one we're going to compare it to is the exponential. So at 0, it's going to be 0.125. At 1, it's going to be 0.25. At 2, it's going to be at 0.5. At 3, it's going to be at 1. And at 4, it's going to be at 2. Now, instead of doing the difference here, you're going to take what's called the ratio. So we're going to take the second one, which is going to be 0.25, and I'm going to divide that by 0.125, and that equals a 2. I'm now going to take 0.5 and divide that by 0.25, and that's going to be a 2. I'm going to take 1.00 and divide that by 0.5, and that's going to be a 2. And then here, if I take 2.00 and I divide that by 2, I mean divide that by 1, that's going to be a 2. So right here, since the common ratio is all the same, this is going to be exponential. An exponential has the form y equals a b raised to the x. Y is equal to 0.125. The b is going to be the ratio, which is going to be 2, and the exponent is going to be x. This happens to be the y-intercept. And this graph's going to look like this. At 0, it's at 0.125. At 1, it's at a quarter. At 2, it's at a half. At 3, it's at 1. At 4, it's at 2. It's going to look like this. It's going to get really, really close to the x-axis. It's just not going to touch it. So if it has a common ratio, then it is exponential. So linear, the first difference has to be the same. Quadratic, the second difference has to be the same. And on exponential, the common ratio has to be the same. We're going to do some examples. We need to determine what type of function the table represents. First, I'm going to try the first difference. So if I try the first difference here, the difference between 3 and 9 is going to be a 6. 9 and 19, that's going to be a 10. 19 and 33, that's going to be a 14. And 33 and 51, that's going to be an 18. So it's not linear. It's not linear. So now let's try second difference. The difference between 6 and 10 is going to be a 4. 10 and 14 is a 4. 14 and 18 is a 4. So now because the second difference is the same, this is going to be a quadratic. On example B, we're going to start off by taking the first difference. So right here on the first difference, the difference between 2 and 5 is a 3. 5 and 13 is going to be an 8. 13 and 30, if I take 30 and I divide by 30, subtract it by 13, that's 17. And if I take 81 and subtract that by 30, I'm left with a 51. Now I'm going to try the second difference and see if that's a constant. That's going to be a 5, 9, and 34. So the second difference is not the same. Now you're going to try the ratio. Now when you're doing the ratio, always take the second one and divide it by the one above it. So I'm going to take 5 and I'm going to divide that by 2 and I get 2.5. I'm doing the ratio. Now I'm going to take 13 and divide that by 5. Now 13 divided by 5, that actually equals 2.6. It's not exact, however, it's really, really close to it. Next, I'm going to do 30 and 13. 30 divided by 13, that equals a 2.31. I'm still kind of really close. And then I'm going to do the last one, which is 81 over 30, and that equals 2.7. These are kind of really close. So the ratios are close enough. This is actually going to be a best fit line. So we're going to go ahead and say that this one is exponential. So first, let's start with the first difference. One and 3, that's going to be a 2. 3 and 9 is a 6. That's going to be 18. And that's going to be 54. Next, I'm going to do the second difference. That's going to be a 4, a 12, and then 54 minus 18 is going to be 36. So it's not second difference. Now, it doesn't automatically mean it's a ratio. Now we're going to try the common ratio. So 3 divided by 1 is 3. 9 divided by 3 is 3. 27 divided by 9 is 3. And 81 divided by 27 is also 3. So right here, this is going to be exponential. Now, the general formula for exponential is y equals ab to the x. The a is going to be the y value at x equals 0. So at x equals 0, the y value is a 1. The b is going to be the common ratio. So my equation here is going to be y equals, the y value at x is 1 is going to be the number 1. The common ratio here is going to be the number 3, and it's raised to the x power. So that's how you write the exponential equation. Example B, I'm going to be taking the first difference. This is going to be a 3, a 3, a 3, and a 3. So because the first difference is the same, this is going to be linear. Now the equation for a linear is going to be y equals mx plus b, where m is going to be the first difference, and b is going to be the y value at x equals 0. So in this case, it's going to be y equals the first difference is going to be the number 3x plus the y value at x is 0, which is going to be a negative 6. You could write it like this, but I know on the assignment online, it's going to be y equals 3x minus 6, because a positive and negative makes that a negative. So that's how you do a linear. Let's go ahead and let's find the first difference. That's going to be a 3, a 9, a 15, and a 21. Let's take the second difference. That's going to be a 6, a 6, and a 6. So because the second difference is the same, this is going to be quadratic. Now, quadratic is going to be in the form of y equals ax squared plus bx plus c. Now, on this one, I'm going to go ahead and you're going to have to solve this by a system. Now, right here, this is the point 0, 0. So x is 0, y is 0. If I plug that into this equation, the y is 0, a I don't know, the x is 0 squared, plus b I don't know, the x is going to be a 0 plus c. Well, a times 0 squared is 0, b times 0 is 0. So guess what? I'm left with 0 is equal to c. So right here, I already know the c value. So it's going to be a 0, which means I don't even need to put this. So now the equation is going to be y equals ax squared plus bx. I'm now going to take the next point, which is the point 1, 3. So here x is 1, y is 3. I'm going to plug it into what I have left in my equation. So the y is going to be a 3. A, I don't know. I'm trying to figure that out. The x is a 1 squared plus the b, I don't know. The x is going to be a 1. When I simplify this, this becomes a 3 equals a plus b. All right, so I have one equation for my system. Let's pull the next point off, which is going to be the 212. So I'm trying to find out what a is and what b is. So let's plug it in. The y is going to be a 12. A, I don't know. X is going to be a 2 squared plus b, I don't know. The x is going to be a 2. So I get 12 equals 2 squared is going to be a 4a plus a 2b. Now, I said you're going to solve a system. You're going to solve that system right there. So I basically have a 3 equals a plus b, and a 12 equals 4a plus 2b. I'm going to solve this by elimination. I want the a's to cancel, so I'm going to multiply the top. Since that's a 4a, I need that to be negative 4a. So this is going to be a negative 12, negative 4a minus 4b. And you actually learned how to do this in Math 1, and actually it's in Math 3a first semester. Keep the second one the same. So now when I add these up, negative 12 plus 12 is going to be, actually, hold on. Let me see here. So that's going to be a 0. Negative 4 plus 4a, that eliminates. And then negative 4 plus 2a is going to be, negative 2b is going to be a negative 2b right here. Divide both sides by negative 2. So then 0 equals b. All right. So 0 equals b. So now I'm just left with y equals ax squared. So now I just need to find out what a is. I can go back and plug in b into one of these right here. I'll plug it into this one. 3 is equal to a plus b. Well, I found b. B is 0. So this is 3 equals a. So now the a value is going to be a 3. So this equation comes out to be y equals 3x squared. So you have to solve it by a system. Last part. We're going to use the function to answer the questions. So if f of x is equal to 3.2x, g of x is going to equal 0.12x squared, and h of x is going to be 2 raised to the x minus 5 power. We need to evaluate each function at x equals 5, 8, and 10. So I'm going to make a table and plug those numbers in. I want to graph on Desmos, and then I want to know when will the function h exceed f and g. So here's f of x, 3.2x, and you're evaluating it. So you want to evaluate at 5, 8, and 10. Now, when you plug in 5 here, you have 3.2 times 5, and that equals a 16. When I plug in 8 here, 3.2 times 8 is going to be 25.6. And then when I plug in 10 here, 3.2 times 10 is going to be a 32. I'm now going to plug those values into g of x. You're plugging in the values 5, 8, and 10. So right here, you're going to do 5 squared, which is 25. Multiply that by 0.12, and you get the number 3. 8 squared is going to be 64 times 0.12. That's going to be a 7.68. And then 10 squared is 100 times 0.12 is going to be the number 12. When you plug in 5, 5 minus 5 is 0. 2 raised to the 0 power equals 1. When you plug in 8, 8 minus 5 is going to be 3. 2 to the 3rd power equals 8. When I plug in 10, 10 minus 5 is 5, and 2 to the 5th power equals 32. Okay, I'm now going to log into Desmos, and we're going to graph these three, okay? So let me share my screen. Here's Desmos. Now I'm going to first graph f of x. F of x is equal to 3.2x. So it's going to be the red line. Next, I'm going to graph g of x, which is 0.12. Now I need to raise that to the x squared. So x, here's my exponent, there's my square. And then on the next one is going to be 2. And now I need an exponent. Now to raise it to the exponent, right here, a to the b power. So the exponent is going to be an x minus 5. So x minus 5. Oh, notice how the minus 5 is not in the exponent. I need to go back and I need to make sure the minus 5 goes up there. Oh, it's not going up there. Okay, so let's put parenthesis minus 5. There we go. So I need to specifically tell Desmos to put that as an exponent. So right here, now the red line is going to be the f of x. The blue line is the g of x, and the green line is the h of x. Now I can also zoom out because one of the questions says, when will the function h, now h is the green, when will that exceed the f and the g? So right here, it's going to exceed it right here because look at the green line. It goes above the blue line right here, and now it's above the red line. So right there at 10. So at x equals 10 is when it's going to exceed both. So I'm going to go ahead and sketch this. Now, right here, if I graph this one first, at 5, it's at 16. At 8, it's about 25. And then at 10, it's at 32. And this one was linear. So this is the f of x. The g of x was quadratic. So at 5, it's at 3. At 8, it's at 7.6. And at 10, it's at 12. So that one looks like this. And then h of x, at 5, it's at 1. At 8, it's at 8. So already, it's already above it. And then at 10, it's at 32. So h of x exceeds both functions after x equals 10. At 10, it's at 32. And that concludes our notes.